Hello everyone, in this video we are going to talk about Turing machines. As this is going to be the last lecture of this semester, I'm going to summarize what we have learned in the course as well before give you the formal definition of the Turing machine. Remember this, this diagram from the Chomsky hierarchy that we have discussed it at the beginning of the semester. So far we have talked about the finite state machines, then which actually represent the regular languages. Then we talked about the context-free languages. So which actually basically the more focus of this course was over these two set of languages. Then in this video, I'm going to just briefly talk about the Turing machine as well. Here I'm going to just emphasize on this fact that except the Turing machine, which is going to cover basically all the problems that we can solve, there are another set of problems that we call them undecidable. And the reason is that because we cannot write an algorithm that can solve them. But I'm going to actually just go back and just a little bit talk about the undecidability and decidable problems, and this fact that although this diagram doesn't really show you, but the finite state machine, the context-free languages, and even the whole Turing machine, which covers all the problems of the polynomial time problems, NP-complete, NP-hard, exponential time problems, the problems that we know that the time that takes to solve them is going to be exponential. All of them are going to be a part of the Turing machine. But still, the set of all the problems which are decidable, which we can solve them, is going to be actually a small set of all possible problems that we can define. Remember, we have, through all the sessions of this course, we have been talking about the languages and problems. Why we are interested in languages? Because we have seen that if we wanted to formally define a problem, basically we show it, we represent it using a language. We define a language to be a set of strings defined over some specific restricted alphabet. Okay, so this is going to be a language. So any subset of possible strings over an alphabet is going to be a language. And basically every language is representing a problem. Some of those problems are interesting for us, some of them are not interesting for us, actually. Okay, so the formal definition of a problem is actually a language. And we have gone through all of these formal definitions and so on. Just we wanted to be able to formalize what can be computed and what cannot be computed. We needed to define some specific notations to be able to write down the formal proofs to show that something is solvable, something is decidable, we can write an algorithm for that, and something is not. Some examples of a problem. Actually, so as I said, every problem is going to be formally represented as a language. Some of the problems which are interesting for us, for example, we check that if a binary string ends with a 0, basically this problem can be represented as a membership problem over a language, that the language of all strings that ends with a 0, and given an input string, we wanted to know that if it belongs to this language or not. So this is going to solve this problem. This is the formal representation of the problem. Or for example, we wanted to check if a number is a prime number. So we can define the language to be the language of all binary strings that represent a prime number, and given an input, a binary string, you wanted to know that if it belongs to this language or not. Or for example, the set, we wanted to check that if a file contains a valid Java program, some Java program without any syntax error. Okay, so you can define the language to be the set of all strings that represent a valid Java program, and given an input string which has been stored over a file, you wanted to know that if it belongs to this language or not. This is exactly actually the task of the compiler that checks if there is a syntax error in the program or not. So, as I said, every program is going to be represented as a language, and basically every language is representing a problem. And it is actually going to be interesting to show you that if we wanted to consider the set of all possible problems, if you randomly choose a problem, if you randomly choose a language, most likely this is going to be a problem which is not decidable. Basically, all those problems that we can solve them is going to be a tiny subset of the all possible problems that we can define. It might not be very intuitive to you because most of the problems that you have already faced are going to be decidable. All the problems that you have solved in your homeworks, in different courses, all the problems that you have seen in different topics of computer science, even in other actually topics of science that can be solved, you can write a program for them. Basically, all of them are going to be just this tiny dot that I write here among all the set of all possible problems. Why I am saying that? Why you might actually just say that how come all the problems that I have seen were decidable? We can write a program to solve them. Yes, but the thing is, the reason basically is that we are not really interested in undecidable problems. If most of the undecidable problems are not interesting at all, that's why you barely actually have seen any problem that haven't been decidable. I'm going to show you a couple of those problems which are undecidable and they are interesting, but most of them are not going to be interesting, and that's why you rarely actually have been encountered with a problem which is undecidable. So a couple of examples from undecidable problems are going to be, for example, if we wanted to check a Java program is going to have an infinite loop or not. Okay, this is something undecidable. You cannot write a program that you pass it a Java program and it can check and tell you that, okay, this Java program is going to actually trap in an infinite loop for some input. It is not possible to write such a program. If we could, that would be very actually interesting and useful. You could have a much smarter compilers. Basically, you could add it as a part of your compiler, and it avoids many semantical errors for us as well. But no, unfortunately, it's not possible to write such a program. This is an example of undecidable problem, which is also actually interesting for us, but you cannot write a program for that. Or for example, we wanted to check if, a problem as simple as this. You wanted to write a program that you pass it a Java program and it should tell you that does this program print some phrase, for example, hello world or not. It might be actually a little bit confusing for you, and you might at first thought that, okay, no, this is not hard. You can write a program to check if a given Java program will print hello world or not. But the intuition is that you should think about it in this way, that your program should be able to check any given Java program will print the phrase hello world or not. And the given Java programs can wait for a long time. You never know. Maybe actually the program is going to have a a very wait for a long time, or for example might actually just trap in a infinite loop. You would never know that when it is going to print a hello world. It's not possible to solve this. Again, I'm just emphasizing that the intuition is that you should think about it in this way, that any program you should be able to check any program, and basically because you cannot check this one, you cannot check this one as well. The reason is that maybe the input program that is given to you has an infinite loop, and you would never know that if you are in infinite loop or if you are still waiting for the hello world to be printed, right? So this problem is not decidable. This was just the intuition, but if you wanted the formal proof why this problem is not decidable, in chapter 8 of your textbook, it's kind of actually try to show you formally why this problem is not decidable and we cannot solve the problem. So basically, if you wanted a more formal proof, refer to the textbook. Or for example, if we wanted to write a program that you give it a context-free grammar, and you want to your program to check if the context-free grammar is ambiguous or not. We cannot write a program for this. These are the set of some undecidable problems which we are interested in, but unfortunately we cannot write a program for them. So if I wanted to show you a more detailed version of that Chomsky hierarchy Chomsky hierarchy, this is going to be a more detailed one. We have seen the regular languages, so basically all those problems that are as simple as they are as simple that can be solved using a finite state machine. So not only they are solvable, but the amount of power that you need to solve them is just limited to a finite number of state. You don't need a stack, you don't need to access to an infinite amount of memory. No, just a finite number of state is going to be enough to solve them. So not only they are decidable, they are very simple. Basically they are going to be definitely solvable in linear time, because you just need to read the input only once. So then next we have seen the context-free languages. These problems are going to be more difficult to solve than the regular languages. You need more power. The machine that can solve these problems are going to be a finite state machine that have access to a stack. So basically you are giving it an infinite amount of memory, but still this is a limited form of power. You cannot have access to the memory as in a regular computer. You have access to the memory, right? You can write anywhere you want. Again, we have some restrictions over how to read the input. You read the input only once from left to right. You cannot read it more than once, and you only have access to a stack just have access to the top of the stack, either read or write from the top of the stack. So this is going to be more power than the finite state machines. So these problems are going to be more difficult, more complicated to solve, but still they can be solved in polynomial time, basically, and using a restricted form of restricted amount of computation power. So then after that, this is going to be the context-sensitive languages. So basically it's going to be all of the programming languages that we have are going to be a part of context language, and there are way more other problems that can be solved in context-sensitive language. I don't want to go through the details because we don't have time, and it is basically just beyond the scope of this course. And then after this level, we are going to have the recursive languages. So what are the recursive languages? Basically, all the problems that you can write, you can write a program for them, you can write an algorithm for them, they are going to be a part of the recursive languages. The amount of actually power, basically the recursive languages are going to be represented using the Turing machines. So if a language is as a recursive language, you should be able to design a Turing machine for that. But the Turing machines are not only going to represent the recursive languages, they are going to represent the other set, which is a superset, the recursive enumerable languages. Because I haven't defined the recursive, the Turing machine, so I cannot really go through more details here. But after that, I have defined the Turing machine. We can just come back and discuss about these two sets: recursively enumerable languages and recursive languages. So basically, recursive languages is going to be a subset of recursively enumerable language. But the important thing to know about recursive languages is that all those problems that you can write, we can write, anyone can write an algorithm for them. It is possible to write an algorithm to solve them. They are going to be recursive. So basically, recursive languages, they are going to be to cover all decidable problems, right? All decidable problem. It doesn't matter how long it would take to solve them. So basically, all the set of problems, the polynomial problems, the NP complete, NP hard, exponential time, all of those problems are going to be a part of recursive languages, a part of decidable problems. It doesn't matter how long it would take to solve them, but because we know we can write down an algorithm to solve them, they are going to be decidable. So those recursive enumerable languages, they are going to be undecidable. And interestingly, there is another set of languages, some languages which are non-recursively enumerable. So basically, we cannot create a Turing machine at all for them. Not only we cannot write a program for them, we cannot create a Turing machine for them as well. So let me actually just stop this discussion about, I just try to summarize what we tried to learn in this course. Now I'm going to just go and focus on Turing machine, and at the end of this lecture I will come back to this hierarchy, just briefly again review what we have discussed so far. So Turing machines, they are not only, a machine like the finite automata, push-down automata, these type of machines. We are interested in these machines not only because they are going to represent a set of problems, but basically they are going to actually help us to define the computation capability, the computing capability in general. So, in the previous slide, I just actually discussed about the decidable problems and those problems that we can write an algorithm for them. So when we are talking about the computing capability, it has actually a formal definition. A computing capability means that we can, something that we can compute, something that we can write an algorithm for that. So if I wanted to give you a more formal definition of an algorithm, so what is an algorithm? So far, informally, you just know that, a sequence of instructions that you can just translate it to some programming language and give it a computer and it execute it, right? So this is an informal definition of an algorithm. But what is an algorithm? An algorithm is going to be a procedure which is effective and computable. What is effective means? We say that a procedure is effective if we can describe it in a finite number of instructions. So the algorithm cannot be an infinite steps of instructions. You cannot actually write an algorithm that cannot be finished. I mean, even the writing, it cannot be finished. Okay, the set of instructions that needs to be done should be finite. Okay, and then it should be well defined, discrete, and the mechanical steps, some steps that you know that a machine can exactly do all of these steps. You know that if from the computer architecture courses, you know that we basically define a set of operations, a set of simple instructions that the computer can do, right? So your algorithm should be written as a finite set of instructions. You should be able to write it as a finite set of instructions, that all of those instructions are discrete, and those mechanical steps are completely clear, what is each step. Okay, you cannot ask your computer to do some instruction which your computer is not able to do it, right? So basically all the mathematical operators and comparisons, read and write, basically that's it. This is going to be the set of all the instructions that each computer can do. We create more complicated instructions, but all of those even more complicated instructions are going to be some procedures written as a simple instructions. And your algorithm should terminate. If your algorithm is going to go forever, so you have a loop that go forever, this is not going to be an algorithm, basically. Okay, so when we are saying to write an algorithm, your procedure, that set of instructions should be effective, which has all these three properties. You should be able to describe it in a finite number of steps. All steps should be well defined, and you should they are going to be those mechanical steps, those simple instructions that can be done over a computer, and it should terminate. It should always terminate, otherwise it's not going to be effective. And the other term that we have is going to be the computable function. Basically, we say that a function is computable if you can write an effective procedure for that. Okay, so this is going to be the definition of the decidable problems. So basically, we are going to say that all the decidable problems are computable functions if you can write an algorithm, you can write an effective procedure to solve them. So all these basically definitions that I give you can be formalized using Turing machine. Turing machine is a form of automata that has basically a very simple definition. I'm going to show you that definition, but it has been shown that everything that can be done using a mechanical machine, a computer basically, can be represented using a Turing machine. So it has been shown this basically the Church-Turing thesis is exactly stating this theorem that if there is an effective procedure to solve a problem, which means that if your problem is decidable, you should be able to write a Turing machine for that halts over all the inputs and solve the problem. So I'm emphasizing on this halts. I know that you don't know the definition. I'm going to discuss it after I gave the definition for the Turing machine. So I'm again trying to say that, okay, all the problems that can be computed, all the problems that you can write an algorithm for them, all the decidable problems can be represented using a Turing machine. You can write a Turing machine to solve it. And this is an if and only if. So if there is a Turing machine for a language that halts over all the inputs, that language is going to be representing a decidable problem. So what is a Turing machine? I have been talking about all those theoretical concepts. Let's just see that what is a Turing machine. A Turing machine is going to be a finite automata that I'm going to show you the formal definition later in the next slide, but the intuition is that this is going to be, we have talked about the finite state. Finite state machines was just a set of states and the transition between them, that a set of finite states and the transition between them. Then we have talked about the push-down automata that have access to, which is going to be informally a finite state that has access to a stack as well. A Turing machine is going to be a finite state that, you are empowered by allowing the machine to have access to a tape, which is from both sides, from left and right. It is an infinite length tape. So basically it's just telling you that you have access to infinite amount of memory. But it is not in a form of a stack, because you are allowed to read and write over this tape, and you are allowed to go to the left and right over the tape. Okay, we don't have the stack as a separate memory, but basically it's just telling you that the memory over the tape is infinite, and you can read and write on that, and you can go to the left and right. So it has more power than just a stack. A stack you can only push to the top of it or pop from top of that. Okay, it is definitely more restricted than a tape that you can move over it to the left and right wherever you want, and you can read and write to the tape. And something that actually about this tape is that the input which is given to you, the input string, has been written over the tape, so it is not a separate tape. Having a separate tape doesn't really going to give you a more power. You can actually define another computation model, but the power of these two machines are going to be the same. So we are simplifying everything, and the input, we are assuming that the input is given over the same tape, and at the beginning when you actually start the machine, when you run the machine, that head tape that you have is going to be at the beginning of, at the leftmost symbol of the input string. And there, how do we know that where the string starts and where the string ends? At the beginning, the state of the machine is that the input have been written over the tape, and on the left of the input there are some specific symbol that we call it the blank. Basically it's just telling you that it is an empty memory. It is a memory that you can read or write on that, but just tells you that this is not a part of the input. And after the last symbol of the input, also the rest of the tape has been marked using the blank. So basically this way you can understand that where the input is going to end at the beginning. And so not only you can read and write on the tape and go from to the left and right, you can read the input more than once. Okay, you can go over the input to the left and right and It's not like the push-down automata or a finite state that you can only read the input once. Here you can actually read the input as many number of times as you want. So the formal definition of a Turing machine is that you have a finite set of states that's going to create that finite state for us. We have an alphabet that input alphabet is going to be the set of the symbols that your input is coming from this set, your input alphabet, and G is going to be a tape alphabet, what can be written over the tape, similar to the alphabet that we have defined for the stack in the pushdown automata. G is going to be the tape alphabet, and usually because the input can be written over the basically the input is given to you, has been written over the input over the tape, so all the sigma is going to be actually a subset of G. And one symbol of the G is called B. This is going to show you that the blank symbol, it cannot be a part of the input alphabet, basically. B cannot be a part of the input alphabet because B is going to represent you where the input is going to end. There is going to be a starting state, very similar to what we have in a finite state, and there is going to be a set of accepting state, although we usually actually have one accepting state in the Turing machine, but you can have more than one. And there is going to be a transition function. The transition function basically going over the at a specific state you are, and the next input symbol that you are reading, and from this you are going to actually move to another state, one of the states from the set Q, and you are writing something over the tape. If you are, for example, don't want to change the tape, you are basically just writing the same symbol that you read, you just write it again, and there is going to be an action over that head of the tape. Either you are moving to the right or you are moving to the left. So basically every move in the transition function can be also showed using this notation, similar to the ID that we have defined for the pushdown automata. It is basically, we usually show the finite at any machine using a transition diagram, right? So a transition like this is showing that the input that you are reading from the tape is going to be X. The symbol, you are at a state Q, the input that you are reading from the tape is X, then the action is you have to write the symbol Y over the tape, and you have to move to this direction. Either this is going to be left or right. In some notations, instead of writing left or right, you can actually you might see that they represent it using the arrow that shows left or right as well. Okay, the instantaneous description or ID for the Turing machine is going to be, for the pushdown automata, we just represent the part of the input that remain, but here we don't, and actually the content of the stack separately, but here it's just like you're combined all of that and show it just using this string. That tells you that the this actually state here, Q, basically tells you that what is the state of the finite state that you are in, and the position that you put that Q is basically just tell you that the next input is going to be xi. You just put it exactly before the next symbol that you are going to read from the input. So the position that you put the cube basically tells where the head of the tape is at. And because we care about the content over the tape, we are going to actually just show the full content here. So basically here it is the full content over the tape is going to be this. Before x1 they are going to be those blank, and after xn they are going to be again those blank thing. You can actually go and write over them those blank items, but if you are writing anything except the blank, they are going to be reported in the instantaneous description. So one move, something like this transition here, that from the state Q over the input symbol X, you move to the state P, and you are moving, for example, to write Y over the tape. So it would be something like this, that you are at this situation like this, that basically this xi is going to be x space, right? This symbol. And after the move, you can see that I have written P, the new state that you are in, and the Y is the symbol that you are going to write over the tape. And you can see that we have moved, the Q was here, right? And now we have moved P to the right, because the transition tells you to move to the right. That's why we put P after Y. If the move is telling you to move to the left, the transition tells you to move to the left, you can see that we can represent it in this way, that you write Y and then you are moving to the left. So the new state P have been represented before this symbol xi. So it's just like you are moving to the left, and the next symbol that you are going to read is going to be x sub I minus 1. So let me show you an example. I'm going to solve and show you a very simple example here. We know that the Turing machines are going to be able to solve any problem which is solvable, but with this very limited, very abstract form of a Turing machine, definitely that's going to be very hard if I'm going to solve a complicated problem. So I'm going to start with a very simple problem. This, the language of n number of zeros followed by exactly n number of ones. We know that this is going to be a context-free language. So it can be used even just using a push-down automata, but this is an interesting example. Because this is going to be a decidable problem, we should be able to write a Turing machine as well for that. So before showing the full machine, the Turing machine, to solve this, I'm going to just give you the intuition, what we are going to do to be able to check if a given string is a part of this language or not. Note that here we don't have access to the stack. I just have the full string written over a tape. I'm going to just give you the intuition, what we are going to do to solve the problem, what we are going to do to check if this string belongs to the language or not. And then after that, I'm going to show you the full Turing machine. Okay, at the beginning, the string has been written over the tape, and the head is referring to the very first, the leftmost symbol of the input. So on the left of 0 is going to be blank. That shows that this is the end of the input. Or basically this is the beginning of the input. Okay, so the idea here is that I'm just actually trying to tell you that what I am going to do, and then we will write the Turing machine for that. I don't have a stack, right? So I cannot, usually when we are going to create a pushdown automata for this language, what we do, we just read all the input symbols, and for each 0 that you see, you push, this was actually the idea, right? For each 0 that you see, you push, for example, a symbol on the stack until you reach to the, for each 0 you push an X to the stack, and whenever you see the first one, you keep just popping the X's from the stack. Okay, and then the next one you pop the next X, you read the next one, you pop the next X, and whenever you reach to the end of the input string, if the stack is empty, you would say that, okay, I would accept the string. But here I don't have a stack. Whatever I have is just this tape. What can I do with that to make sure the number of zeros is exactly equal to the number of ones, and all the zeros at the beginning, all the ones are at the end? One thing that I can do here is that I can start, I'm going to actually just basically do the same concept as what we did using the stack. But instead of having the stack here, what I can do is that I'm going to just replace these zeros with an X, okay? And then go forward, find a 1, and whenever I found a 1, I will also mark that one as well. But probably I need to actually use a different symbol. For example, for all the ones, I'm going to actually, just let me actually use a different color. So I'm going to replace every 0 with a X, and then go forward, and whenever I see a 1, I will replace it with a Y. Then I just go back and find the next 0. I'm going to go back to the very beginning and find the next 0. So basically I'm going to go back until I find an X, which tells me that this is the last 0 that have been changed to X. Then you actually go one move back, then change this one to X, then you go forward until you find a 1, and then replace it with Y. Then you go again back and find an X that tells you that this is the very first X that you see. This is going to be the last 0 that has been changed to X, right? So then you move one step back and then change, if there is an X, if there is a 0, you replace it with an X, and then you go forward and find a 1 and replace it with Y. So, and then when you change that, you are actually going back to find a 0. If you didn't find a 0 before seeing an X, it tells you that the number of zeros has been finished, right? I don't have any other 0. Then at this step, you should actually go back and then see if there is any other one or not. If there is no one and you reach to a blank symbol, it means that yes, the number of zeros and the number of ones are basically going to be the same, and you have actually marked all of them. So this is going to be represented, in these steps. I'm actually showing all of these steps through this set of slides. You replace the first 0 with X, then you go forward until you find the first Y. You change it to Y. It's just like you are counting. You change that 1 to Y. Then you go back to find the next first 0. So this is actually represented in 2 steps. You go back to the very first X, the closest X that you find, then you move to the right to find the next 0, put an x instead of that, write an x there, and then go forward and find the next one, which is going to be this one. You replace it with y, and then again you go back to find the next 0, you replace it with an x, then you go to the right to find the next one, you replace it with y. Then what you do is that you have to go back, check if there is no other 0. If there are some actual zeros remains here, that's going to be an issue, right? Then you actually go back and check that there is no other 0. Whenever there is no other 0, then you go forward to the end to check if there is no other 1 at the end. And if not, you would say that you would stop and you would accept. This is something that I'm going to implement. Then I'm going to now showing the full transition diagram for this Turing machine. Okay, it shows the full the transition diagram. It might not quite intuitive at the beginning when you are looking at it, but let me just explain that the algorithm that that intuition, that procedure that I explained before, I have written it here. It is actually the 3 basic move that you mark the next unread 0 with x. So basically that's going to be the state q0. You are at a state q0, and it is just like you are at the beginning of the input string. If you see a 0, you replace it with an x, and what you are moving to the right. Okay, you see that this is the transition. This is exactly the transition that you write. The next input symbol should be 0, okay? And you replace it with a x, and then you move to the right. Okay, this is the next actually step that you do. And so basically you are moving to the state q1. So in state q1, what you are doing is that you keep moving to the right, okay? You keep moving to the right to find the very first one. In between, you might see some other zeros, something like actually what we have here, right? You have to move forward, and in between, you might actually see some other zeros. So that's why you can see that if you see another 0, don't touch it. Just rewrite 0 over the tape and keep moving to the right. Okay? And whenever you see the very first one, you replace it with y over the tape, and you are this time, instead of moving to the left, to the right, you are moving back to the left because you wanted to go and find the next 0. And so that's why we are moving to the next state as well. So the next state is going to be a state Q2. So in the state Q2, which actually represented in this way, what you are doing is that you keep moving to the left. You keep moving to the left to find the very first symbol, the very last symbol x that you have written. Okay, so basically you don't touch the content. So this is this step, right? This step. That after you have written the y, you have to go back to the left. So in between, if you have seen any other 0 or y, you don't touch them. You just rewrite them over the tape. You are not counting here. You just are going to the left to find the next symbol 0 from the left to be able to actually count it, right? So what I'm going to do here is that if in between you are seeing a y or you are seeing a 0, don't touch it. Just keep moving to the left. Okay? Whenever you see the very first x, so in that tape that I actually showed you there, so just assume that this is, for example, you are at some situation like this. okay? You go to the left, and then whenever you see an x, it is telling you that, okay, I have seen the very last x that have been written, right? So it's just like you are going to go back to the very first step, that replace the next 0 with a 1. So you move to the state q0, and you don't touch that x, but you are changing the direction. So basically you will be in this situation again. So at state q0, again, your action is, okay, you have seen, if you see the next 0, you would replace it with an x, right? And you keep moving to the right, and you move to the state q1 as well, which is the state of moving to the right until you find the very first one. So whenever we are done, we are finished. So here you are replacing this one with a y, then you keep moving to the left, okay, moving to the left until you find you reach to the x, then you go back, you replace this one, then you go forward until you go to the right until you find another y, you replace it with a y. Then actually let's see that what would happen in this case. So far what we have done is that all the x's, all the zeros and all the ones have been replaced with x's and y's. So after this state, after you have replaced the last one with y, you are moving to state q2, right? And then at the state q2, you keep moving to the left. You keep moving to the left, not until here. You keep moving to the left until you reach to finding an x. So by finding the very first x, you are moving to the state q0. At state q0, if you see a 0, you move to the q1, but there is no other 0, right? You are here, and there is no other, you have moved to q0, so basically you are here. There is no other 0, right? We are done with reading all the zeros, and we reach to the beginning of the ones that have been replaced with y. You are at q0, and the next symbol that to be read is a y. It tells you that, okay, I'm done with reading all of the zeros. What remains here is that I have to go back, right? All the zeros has been marked, and I have replaced all the ones with y as well. What I'm going to do is that I have to go to the right, but this time I'm not searching for a 1. I am moving to the right until I find a situation that there is a blank, but there is not a 1 at the end. So you move to the right. In the state q3, you keep actually moving to the right. Whenever you reach to the end of the string, everything has been replaced. All the ones have been replaced with a y. If there is a blank, it tells you that you have replaced all the ones. You have replaced all the ones, and all of them have been actually corresponding to a 0. And then after that, you move to an accepting state. And yes, you accept the string. What would happen if there is, let me actually just clean up a little bit here. What would happen if there are more ones than zeros? So for example, if there are another 1 here after the number of y's that you have checked. If there is a y here from q3, there is no move over a 1. There is no transition from Q3 that can actually move, that can read a 1 from the tape. Because there is no transition, it's going to actually crash. What would happen if there is a 0 here? Again, if there is a 0 here, the string is not going to be, for example, you have seen a string like something like this. This is not in the language, right? Because there is no transition on Q3 over the input 0, the machine is going to crash, and just tells you without going to an accepting state, the machine is going to crash and you are going to reject the string. So if there were more zeros in between, so a situation like this, if it happened that, for example, you have a situation like this, that the number of zeros is more than the number of ones, something like this. What would happen? So here in Q0, after you replace the last, for example, this 0, you would replace it with an X, right? And then you go to the Q1. In Q1, you only can move to the right if you keep actually either seeing zeros or Y. Okay, so in that case, what would happen? Because there is no, you would actually just, there are some actions here. You can actually go forward until you reach to the, you go forward and there is no action, there is no, transition over Q1 and there is no transition over Q1 and B. So if you go forward until you have seen Y and you don't see a 1, you suddenly actually reach to this state that you are seeing a B. It means that you haven't found a 1. It means that you have marked a 0 and then you come back to count the corresponding 1 and you didn't find that 1. The machine is going to crash. The machine is going to crash here, and so this is going to reject the string. This is not an accepting state. So basically this set of transitions shows that how the machine is going to read and accept a string like this string, okay? You can represent it as you start at a set Q0, right? The next symbol that you are going to read is going to be this symbol 0. Over the moves, you would replace 0 with X and you are moving to Q1 and you are moving to the right. So you put Q1 after the X and the rest of the string is going to be 0, 1, 0, 1, 1. And then at Q1, you keep actually staying at Q1 with seeing a 0 and you don't actually touch it and you go to the right. So you stay at Q1 and you just pass the next one. Then whenever you see a 1, you move to Q2 and you switch the move, you transit to Q2 and you switch the move. So you move to the left and you write Y. So this is the situation that you have written a Y and you move to the left. And then after you move to the left in Q2, you keep moving to the left by seeing any 0 or any Y. Okay, so this actually shows you the situation that you move to the left. And whenever you see the first X, you move to the right, don't touch the X. And whenever you see the next 0, you keep moving to the right and replace that X with a 0. That's 0 with a X. Actually, it's just showing all the steps. I think if you follow the steps, you can. It should be quite clear what's going on. This state diagram that we have seen here can be written as a table But you can see that the table is going to be much bigger and probably much harder to read, so definitely this state diagram is going to be preferred. If you are writing a Turing machine, that's much easier to represent it as a state diagram than the table. Something about the Turing machine and the accepting situation. There are some differences between accepting a string in a Turing machine and the other machines that we have seen, the finite state or push-down automata. We are saying that in a Turing machine, if we reach to the accepting state, if we enter to an accepting state, the machine will stop. The machine will stop and tells that we accepted the string. It doesn't matter what is the situation of the content of the table. As far as you reach to a state which is an accepting state, the machine will stop and will accept the string. So we are actually saying that the machine will halt. The machine stop, the machine will halt, and it accepts the string. So that is actually the difference. If there is no basically for the Turing machines, we don't define any transition for the accepting states. After you enter the accepting state, any accepting state, the machine is going to stop. That's why at the beginning I told you that just one accepting state is going to be enough. And the accepting states in the Turing machine doesn't have any transition, unlike the finite state or the push-down automata, that even if you enter to the Turing machine even if you enter to an accepting state, if you haven't finished reading the input, you still need to actually continue, and that's why over the accepting states you might have some transition in a finite state or in a push-down automata. But in the Turing machine, that's not the case, because the input string has been written on the tape. Basically, there is no concept of reading the full string. Whenever you enter, and this is just a definition, okay? Whenever you enter to a final state, the machine will halt and it will accept the string. So you should put that transition to an accepting state as the last step. Whenever you are sure that you are going to accept the string, just in that case, you move to a final state. Some other note about how the Turing machine is going to work is that it is possible for the Turing machine to trap in an infinite loop. It means that you actually go over, you actually just keep moving over the transition, the finite state, and never enter an accepting state, and always there is a transition to move on. So in that case, you will be actually in an infinite loop. Or you can reach to some state, and if there is no transition defined for the situation that you are in, so your Turing machine will stop. Your Turing machine will basically is going to crash, and because the state is not an accepting state, your Turing machine is going to reject the string. Okay, so there are two different situations except accepting the string. There are two other situations for the Turing machine. In a finite state machine or in a push-down automata, either you accept the string or your machine is going to crash at some point and you reject the string. There is no other possibility. But in the Turing machine, there is some other possibility. You actually just stick in an infinite loop. It is possible that you to define some Turing machines that over some input string, it never enters to a final state and it never crashes. It actually keeps moving over the states forever. So that's going to be an infinite loop. So in that case, we will say that your Turing machine is not going to halt, doesn't halt. If you reach to an state and there is no transition over that state for the situation that you are in, your machine will crash, your machine will stop, okay? So, and reject the string. So this is where exactly we define the recursive languages, something that I have actually just discussed, those recursive languages and recursively enumerable languages. So as I said, the Turing machine is going to represent a set of languages that we call them recursively enumerable. So a language is called recursively enumerable if we can design a Turing machine for that language so that all the strings that are accepted by the Turing machine are going to be a part of the language. So you see that it doesn't tell you what would happen for those strings that are not in the language. So your Turing machine can go and stay in an infinite loop if the string is not a part of the language. If the string is not a part of the language, your Turing machine can go in an infinite loop. So that's bad, because basically you would never know that if the data string belongs to the language or not, because your machine is going to go in an infinite loop. But for all the strings belong to the language, definitely the Turing machine will go to the final state. Okay? For some of the languages, some of the strings which are not in the language, your Turing machine can go to for the strings which are not in the language, the Turing machine can either go to an infinite loop or crash or halt. Okay, so this is the definition of recursively enumerable. But if a language, you can actually create a Turing machine for the language so that the Turing machine accepts all the strings belong to the language, and the Turing machine will halt over all the strings which are not in the language, that language is going to be recursive. So basically that's going to be exactly the decidable problems. Any problem that we can write an algorithm for that. And I think now it is clear. If you can write an algorithm for the problem, for every input string, your algorithm either accept or reject. So definitely it's going to have an answer. It's not going to go an infinite loop. So the recursive languages are going to be the decidable problems. Everything that we are basically interested in real world, and I shouldn't say interested, I should say that most of the problems that we are interested in real world, and all the problems that we can write an algorithm to solve them in real world. Just before I actually finish this lecture, I wanted to shortly talk about, briefly talk about the P, NP, and exponential time problems. All of those problems which are P, NP, exponential time, all of them are going to be a part of the recursive languages. The set of P are those problems that you can write an algorithm in polynomial time for them. We can write we can actually write a program that works and runs in polynomial time problem. So basically everything that we have discussed in this course, not only those, more than that, are going to be a part of the polynomial problems. The context-free languages, the regular languages, all of these are as simple as, can be solved in at most n power 3 in terms of the length of the input string actually. That can be solved in at most n power 3. So all of them are going to be polynomially solvable. They are really simple problems. Okay, we have a set of problems which we call them NP. Those problems, we don't know if there is a polynomial time solution for them or not. Yet actually no one have found any polynomial time algorithm for them. There are some exponential time algorithm for them, like for example, the traveling salesman problem. All the NP complete and NP hard problems are in this set. I'm not going to discuss about them. It's just to tell you that where these problems are exactly in this hierarchy and what would happen to them. And there are a set of problems that we know how to write a algorithm for them, and we know that the algorithm to solve them is going to be definitely exponential time. We cannot write anything better than that. So all of them are going to be a part of the recursive languages, basically. Usually when we talk about the theory of computation and the complex, the theory of the complexity theory, these are completely different things. When you are talking about how hard it is to solve a problem, you are talking about the complexity of the problem. If either it is polynomial, if it is NP, if it is exponential time. So you are talking about the complexity of solving it. You are not talking about if you can solve it or not. In the theory of computation, basically we are talking about more general concept. We are talking about the whole hierarchy here. The problems which are decidable, the problem which are a part of different actually set of this set of regular languages, context-free languages, context-sensitive, and basically we are talking about the capability, the computation capability, what problem we can solve, and then we also actually talk about how hard each problem is. Then based on that, it actually become a part of any of these subsets. Okay, before finishing this lecture, you see that we didn't really have time to cover the Turing machine in much detail, or about the decidability, undecidable problems, and so on. The reason is that all of them are going to be beyond the scope of this course. This course was more like an introductory to the computation theory. So you have learned about the regular languages and context-free languages in details. And now in this last lecture, I just tried to tell you that the big picture, where all of these problems, these regular languages, context-free languages, and decidability, recursive languages, and so on, are going to happen. Just one more term that you might actually hear a lot you would definitely hear a lot in the theory of computation, and that term is the halting problem. We have actually talked about this problem, that this notation that either the Turing machine is going to halt over an input string, or it goes to an infinite loop, right? The halting problem is exactly related to this problem. Informally, but practically, I can define the halting problem in this form, that you have a program, or basically you can think of it as the informal form. You have a program and an input I. You wanted to know that if your program is going to an infinite loop, or it will terminate over the input I. Okay, so this question is not decidable. We cannot answer this question. The formal form, the theoretical form of this question or halting problem is that you have a Turing machine that has been defined over some alphabet, and you have a string from that alphabet. You wanted to know that does your Turing machine halt over this input string or not. You wanted to check this. Okay, so this is the halting problem. you have a Turing machine and you have a string. You wanted to know that if this Turing machine is going to halt over this string or not. Usually, when you have a machine, for example, when you had a finite state machine, when you have a push-down automata, what you were going to do? You would give and then you wanted to actually ask that if your finite state is going to terminate over this string or not. You could simply check that by run your finite state, by run your push-down automata over the string. And basically it would definitely terminate. Either it is going to accept the string or reject it, but it would actually terminate. It will stop, right? But in the case of the Turing machine, this is not as simple as this. You can run your Turing machine over the input string, and your Turing machine, if the Turing machine just go on an infinite loop, it's never going to halt. And you don't know when you have to stop, right? You go forever and you would never know that when it's going to stop. Maybe it's just taking too long. You would never know. That's why this is not decidable. So this was the halting problem, actually. But there is another problem that, something similar to this, something related to this, but this one is decidable. That you have a Turing machine and an input string. You have a Turing machine with one final state and an input string. You wanted to know that if this string belongs to the language or not. This problem, you can actually see that this is exactly similar to the problem of you have a finite state, deterministic finite state machine, and you have a string. You wanted to see that if the machine is going to accept the string or not. Okay, this is decidable, definitely. As I said, you can solve this as simple as just run the DFA over the string. It's going to either accept or reject it. But the halting problem is not decidable. Again, I'm just trying to emphasize on this fact that because your Turing machine can represent recursively enumerable problems, it is possible that your Turing machine go on an infinite loop. That's why you cannot even check if the Turing machine is going to halt over a string or not. If the language is recursive, yes, this is going to be decidable. But if the language is recursively enumerable but not recursive, the halting problem is going to be undecidable. So this is going to basically cover chapter 8. I tried to just briefly talk about some concepts of decidability as well from chapter 9, we didn't cover chapter 9 in this course.